Okay. So, so previously we were talking about the electric flux. We went through the Faraday's experiment and the Gauss law. We said that um, uh, as per law, the electric flux is equal to, or the total lines of forces that pass through a surface is equal to a total charge enclosed in that surface or in that structure. Okay, that was the Gauss experiment, and Faraday worked on a similar concept, and he ended up on the displacement of flux. So he at that time defined it as the displacement density. Today we know that it is the electric flux which moves from positive charge and ends on the metallic plate, thereby creating a potential difference at that point, thereby creating a charge separation at that point. So that was the Faraday's experiment. And we saw this for spheres, right? We saw this for spheres, but we can extend the result of the spheres to a coaxial cable, right? So previously, we were looking to find the electric field due to a line full of, say, positive charges, right? So if this was the line full of positive charges, its electric field will always be perpendicular in all possible directions, towards me, towards the board, and in all possible direction. And that electric field will be equals to rho L. Rho L is the charges on the length of the wire. So rho L divided by a constant 2 pi epsilon naught divided by 1 over rho, where rho is the distance. Okay, rho is the distance, and this one is the line charge density. This one is the line charge density, and this one is the radial distance from axis of wire. Okay, so the electric field due to a wire line is inversely proportional to its distance, right? So that was the thing which we were working previously. Then we said, what if we place another metallic cylinder around around this wire? Now, what if we place another metallic, suppose this one, cylinder around this structure? Okay, so we will end up on the say this is also wire or metallic. Okay, then this electric field which is going out will end on this sheet, on this outer sheet, and the strength of this electric field will be E equals to rho L divided by 2 pi epsilon naught divided by rho, in the direction rho. So this is a vector quantity, and this field will end on the outer wire, and this new structure is now called as coaxial cable. So now if we have this coaxial cable, you can see that it's the inner inner wire has a radius a, and the outer wire has a radius. Uh, the outer wire has a I guess this PowerPoint version is a little older one, so I have a little incompatibility with my pen. So this outer wire has a radius rho equals to b, inner wire has a radius of a. So you can see that the electric field is E rho in the direction rho. It's a vector quantity. It will be rho L divided by 2 pi epsilon naught divided by rho in the direction rho. So the electric field, as it moves from the inner wire to the outer wire, the electric field will decay. The electric field will be perpendicular at every point, perpendicular to the inner wire at every point, and it will decay. It will decay with the rho. Okay, and rho lies between, rho is greater than uh, rho is less than B and is greater than A. Sorry. So if you look at this structure, this is the amount of the electric field. Now, if I bring this epsilon naught on this side, uh, we will have epsilon naught E rho in the direction rho. It will be rho L divided by 2 pi and rho in the direction rho. And this will be equal to D equals to rho L divided by 2 pi rho in the direction rho. So now this is electric flux density. Now this one is the electric flux density, which equals to rho L divided by 2 pi divided by rho. Okay. Any question here? No question. Okay. So this uh, any question, by the way, to this point?
No, sir, no questions.
Okay. Can anyone tell me who is absent today? Okay, we'll leave it. We'll short that, sort that out later on. Okay. So the D on the inner surface, and if you again look at the same equation, this one, uh, this equation is rho L is how much? Q divided by line length of the coaxial cable in the direction rho divided by 2 pi rho. Okay. So so if I take this here, D equals to uh, charge divided by length divided by 2 pi rho in the direction rho. I can write it like charge divided by 2 pi L. L is the length of the wire divided by rho in the direction rho, and it's D. Okay. Now, from here, our Q is equal to D 2 pi rho L. Okay, 2 pi rho L. This is charge. Okay, D is 2 pi rho L. Okay, any question here? This is charge now. This is charge. Okay, this is the total charge. Okay, and this one is the so charge on the inner sphere equals to D 2 pi. What is rho for the inner sphere? Rho equals to A. This implies that Q on the inner surface equals to D 2 pi A L. Okay, 2 pi A L. Okay, 2 pi A. 2 pi R is the circumference, right? And if you multiply it with the L, it will give you total area. Okay. Uh, if I bring it here, what is 2 pi A? circumference of wire 2 pi L, 2 pi A into L is what? Total surface area of wire. Is this clear? 2 pi A, where A is the radius. 2 pi A is this is 2 pi A. If I take all the circumferences, the length of the wire, I will multiply with if I take all the circumference, I will multiply with L to get the total surface area. Okay, is this clear?
Yes, sir.
Surface area of the wire. Okay, so you can safely say that charge equals to D into area of surface area of wire. Okay, surface area of wire. Okay, and if you bring it Q divided by surface.
सर ये surface area या curved surface area होगा ये?
Sorry,
ये जो आपने फॉर्मूला लिखा है ये कर्व सरफेस एरिया होगी या टोटल सरफेस एरिया? क्योंकि सर
ये
टोटल सरफेस एरिया के पास
हाँ हम टॉप साइड जो है. ओके, लेट मी टर्न ऑन कैमरा. कैमरा कहाँ से ऑन होगा बाय द वे? हियर लुक हियर the surface area of this wire, right? The entire surface, not the surface area of the top, not the surface area of the bottom. Are you getting it?
ओके
We are not
यस
interested. There is no electric field in this direction, no electric field downward. Only the electric field is going in the perpendicular to this surface, this cylindrical surface. Okay.
ओके थैंक
Welcome. Okay. So again, this is your surface area of the wire, and now you can see that charge divided by surface area of wire, charge divided by surface area of the wire from this equation, yeah, is equal to D, which equals to rho S. Okay, is this clear? Okay, so this is already known to us. And shortly we'll see this green equation which I just wrote in a more general way. We'll shortly see that. Okay, because we will look for the same equation right from this point to end on this point. Okay, so so our charge is equal to D 2 pi rho L. Okay, this is the equation we from last page. We found this equation on the last page. Okay, now the total charge is how much? Total charge is how much? Right? Because rho L, what we say, charge is surface charge is charge divided by area. Okay, so if it is differential charge, you have differential area. So dq equals to rho S d area. Okay, this is the area. So charge is equal to integral rho S dA, right? This sort of equation. Okay, so if you are looking for the total charge, look, this equation is equal to ds 2 pi rho L. Okay, And what is ds? What is ds? What is ds? ds is rho s, surface charge density. You remember psi equals to integral d dot ds equals to charge. You remember this equation? This is the Gauss law, Gauss equation. So psi equals to this thing. Okay. So psi is equal to psi equals to d dot area. Okay, equals to total area. If you integrate it, you will get the total area. Okay, you can safely knock out this d from here, and the integral, the surface integral of ds, which is the area, equals to charge, right? Or you can say psi equals to psi divided by area equals to d, or you can say it is charge divided by area, or equals to rho s, surface charge density. So this is something which we know from our previous chapter. Okay, so look again, uh, is rho s is for ds, 2 pi 2 pi rho into l. Okay, 2 pi rho into l. So if you consider the inner conductor, for inner conductor, rho equals to a. So q inner is how much? Rho s 2 pi a l, from this equation. Okay, from this equation, this equals to q. Okay, from this equation. Okay, so and q for outer conductor is rho s 2 pi b into l. This is for the outer conductor. Okay, inner conductor, outer conductor. Okay, outer conductor. And we also know that q equals to psi. So psi equals to from this equation, psi, which is the electric flux, equals to rho s 2 pi rho s 2 pi rho into l. Okay, or you say psi divided by 2 pi rho l equals to rho s, which equals to charge divided by 2 pi rho l. Okay, so you have all these equations. You have all these equations moving from and for this is the condition. This one for the gap between gap between inner and outer conductors. Okay, inner and outer conductors. So little bit mathematics, and you can see many things in this equation. Okay, any question here?
No, sir.
No. Okay.
No, sir.
Okay, so this we proved on last page. We showed this equation on the last page. D is equal to rho L over 2 pi, because what we did, um, we just brought this epsilon naught here, and we get this equation, which is D rho L divided by 2 pi, right? Okay, So so that was the uh, that was the uh, that was the equation of the coaxial cable. Now, if you take this inner Q inner, if you take this equation and this one, if you take this one and this one, you'll have a little negative sign. Why? Because if suppose you have here positive charge, here you will have negative charge. Yeah, negative charge on the inner surface. Okay, so this Q outer is with negative sign. Okay, this Q outer is with the negative sign. Taking these two equations combined together, you you end up that the Q outer is 2 pi A L rho S, last page. Okay, from this one, on this page, right? And Q outer and Q inner, right? So combining these two equations, I will put star here. Combining the star equations together from last page, or I put combining these two equations from last page, we get that the Q outer charge on the outer cylinder is equal to minus 2 pi A L rho S of the inner cylinder. Okay, is this clear? Or you can say, if you combine those two equations together, you say 2 pi B means the outer, L is the length of the cylinder, rho S outer cylinder is equal to minus 2 pi A Ls, because charge will stay the same but with just a negative sign. Okay, so if you combine these two equations, you say Q inner is equal to Q outer but just with the negative sign. Okay, so what that means? That means that rho S 2 pi A L equals to Q outer minus rho S 2 pi B into L. So this is the equation. Okay, because charge is the same but just with the opposite sign. It's that only difference. Okay, charge is the same but just with a negative symbol. Because if you go back to the Gauss law and then the Faraday's experiment, you see that if you have the positive charge here, this positive charge here, you end up on a negative charge here. Okay, so just the same amount of charge, but the only difference is you have the opposite symbol. Okay, the opposite symbol you have. That's it. So this is from last page. This equation is from last page. So little bit, if you can knock out this 2 pi with this 2 pi, L with this L, you end up that B rho S outer equals to A rho S inner, the negative sign. Okay, or you can say that rho S outer is equal to minus A by B, the ratio of the two radii inner, ratio of inner radius to outer radius. So this is one very uh, important parameter in design in design of coaxial cable. So this is one very important parameter in the design of the coaxial cable, that the ratio of the two radii will play this kind of role. So whenever you design, later on we'll see the full design equations of the coaxial cable. Later on we'll design the coaxial cable for specific design parameters. And we will be using this ratio A to B. This ratio plays an important role. If you change the radius of A or radius of B, you actually design everything. You change every aspect of your design. Okay, the coaxial cable, and the design parameter important. The design parameters. The design is characteristic. You design coaxial cable for characteristic impedance. Okay, you design the coaxial cable for characteristic impedance, and this is one important parameter, characteristic impedance, uh, for which we design our communication links. Okay, characteristic impedance is a very important parameter, and later on we'll see that the ratio of A to B plays an important role in characteristic impedance. Any question here, by the way? Any question?
No, sir.
Uh, uh, is everything clear, or you don't want to,
Yes, sir.
you don't want to ask anything?
All okay, sir.
All right. So characteristic impedance is an important parameter for the design process of the coaxial cable. Okay. Okay. Coming back to the lecture. Now, this one more concept regarding the flow of electric field, right? And that concept is in a mathematical parameter called as divergence. Okay, so what the divergence? Why we take the divergence? Okay, previously, if you know the Gauss law was equal to total charge enclosed. Okay, that was the Gauss law. Okay, but there was a person by name of Maxwell. He said this is a very good equation because it relates a physical quantity charge to a non-physical parameter psi. But he said this is not giving us enough information. And he said, I need to investigate this equation in coordinate system. So he put this equation in a coordinate system. That's the only difference Maxwell brought. He studied this equation in a coordinate system. He was in opinion that we must locate the position of the charge, and then we shall see how much field is moving out or moving into that point in space. Okay, so he said, okay, fair enough, charge equals to psi, but where is the location, where is the charge, and where is the psi? So he said this equation is missing some important information, so he put this equation in a coordinate system. He translated this equation to a coordinate system, to a space, because this equation doesn't have the time, doesn't have the space. Now he put it in the space. Okay, so what he did, when he put it in the space, he tried to investigate this equation in space. So for that purpose, he said, for example, we have some differential volume of charges. Say this is full of charges. Okay, differential volume of charges. So we have some differential charges here. Differential y, differential z, differential x. Okay, differential x, differential z, and it's going to create a volume. Okay, so then he said the D field, which may go in this direction, or which may go in this direction, or which may go in this, or which may go in this direction. So how to find the different locations? Okay, for that purpose, he said this D at any time may have three components: dx, the direction x, plus dy, the direction y, okay, and the dz in the direction z. So that he was in the opinion that he wants to study this thing. Okay, so psi, as was known, so psi equals to charge, differential psi equals to differential charge. Okay, differential psi equals to differential charge. Okay, so psi equals to differential charge, which equals to volume charge density rho v, and the differential volume. This is the differential volume. Differential volume equals to differential x plus differential y plus differential z. Okay, this is x. Okay, differential x. Okay, so that he want to study in a coordinate system, and he said if you do that, the divergence equals to rho v. Now, what is the most important parameter which defines this thing? It's the del parameter, del operator. It gives you change in the x direction plus change in the differential change in y direction plus differential change in z direction. So this is the divergence. So when you combine the uh, divergence with the Gauss law, you end up on something new. Okay, you end up on something new. Okay, any question here? So psi equals to integral d dot ds, which equals to charge. So psi equals to d integral ds, which equals to charge, where ds is the area. So psi equals to d dot area, which equals to charge. Okay, so psi divided by area equals to d equals to charge divided by area, which equals to rho s. Okay, so vector quantity. Okay, so vector quantity. Do you understand this equation? Okay, now look here, if I try to put this thing psi divided by area and charge divided by area, if I try to put it in a coordinate system, so what I would do, I would apply the divergence. Okay, now the space coordinate is like the del operator. The space is just like a del operator, which is partial by partial x in the direction x plus partial by partial y in the direction y plus partial by partial z in the direction z. If you see closely, this is z direction. Okay, what is partial by partial x? It is 1 over 1 over length plus 1 over length plus 1 over length, where length is the length is dimension of x, y, and z. Length is dimension of all these things.